Okay, I'll try and say a lot of the words. Sure.
What's that? Is that an infinity?
No, that's the alpha.
Oh,
But the concept was too long, I don't wanna rewrite it.
Okay, so so I was gonna talk more about partial fractions, but there was a question first. I think it's worth looking at. So the integral that you were looking at was, what was it, 1 minus x squared, so 3 has power.
Oh, yeah.
Yeah.
I hate that.
Yeah. So we let x equals sine theta.
Oh my God, really good.
So then this becomes, what? 1 minus x squared is sine, 1 minus sine squared, so it's cosine squared. So 3 halves, and then you have another cosine, which is terrible. Then you're gonna have the integral of cosine to the fourth, right? Nobody likes. So then, and sorry, Gia, if you have questions, make sure you definitely chime in, ask for clarification if you need it. We'll try to make it, I can't imagine you can see very well, but you can certainly hear the words I'm saying. So we're integrating cosine to the fourth, which is cosine squared times cosine squared, which is then going to be 1/2 times 1 plus cosine 2 theta. Times another 1/2 times 1 plus cosine 2 theta. So do that. I'm just using the trigonometry, the cosine squared theta is 1 plus cosine 2 theta over 2, squaring it, bring out the 1/2. So then. We have to use that trigonometry again. So we're going to multiply that out. We're going to get 1/4 integral of 1 plus 2 cosine 2 theta plus cosine squared of 4 theta. That's 2 theta. Then we do the same thing over there. So that's going to be 1 plus cosine of 2 times 2 theta over 2. I like to make the move here where I factor out a 1/2. I'm gonna say I've got a 1/8 times 2 plus 4 cosine theta plus 1 plus cosine of 4 theta. I feel like I've done this one before. Yeah, it is.
How come you have to multiply everything by 2?
Because I factored out a 1/2 just to make so I didn't have fractions to deal with. Like I could say I've got 1 plus 1/2 is 3 halves, and then 2 cosine theta, 2 cosine 2 theta plus cosine 4 theta over 2.
Yeah.
But then I would rather just have 1/2 out of stuff. And then we can finally integrate. We get 1/8. 2 plus 1 is 3. The integral of 3 is 3 theta. Integral of 4 cosine 2 theta is 4 sine 2 theta over 2. And integral of cosine 4 theta is sine 4 theta over 4. And then, yeah, distributing and writing things since we get 3/8 theta, 2/8, so 1/4 sine 2 theta. And then 1/8 times 1/4 is 1/32 sine 4 theta. Okay. And then if we want to turn things back into x, this is where things get messy. So, yeah, I'm gonna erase over here. So specifically, yeah, I'll talk about you. Specifically, using the fact that x equals sine theta, sine theta equals x over 1. Draw the triangle. Sine is opposite of the hypotenuse. The third side is always the square root that was in your integral. Or you can do Pythagorean theorem. Then, and this actually comes up more frequently than I would like it to, personally. You have to use the double angle identities to deal with sine of 2 theta. Right? You can't say sine of 2 theta is 2x. Not right. Sine of 2 theta is some other angle over here, it's 2 theta. So we're going to say that sine of 2 theta is equal to 2 sine theta cosine theta. So that'll be specifically 2 times sine of theta is x. Cosine of theta is the square root of 1 minus x squared. That's not so bad. what sine of 4 theta is. Sine of 4 theta is sine of 2 times 2 theta, which is 2 sine of 2 theta times cosine of 2 theta. And then you have to use the double angle identities for sine and cosine. So, yeah, I know, fun times, right? You get 2 sine, oh, sorry, you get 2 times sine of 2 theta is 2 sine theta cosine theta. And cosine 2 theta is cosine squared theta minus sine squared theta. There are other versions of this, that's the first version I can show. So we get 4 times sine of theta, which is x, cosine of theta, which is the square root of 1 minus x squared, and then cosine squared, which is 1 minus x squared, and sine squared, which is x squared.
So what exactly is the double angle term?
I wouldn't say theorem, it's a formula. So the double angle formula, for sine and cosine is sine of double an angle is 2 times sine of that angle and cosine of that angle. And cosine of double an angle is cosine squared of that angle minus sine squared of that angle. So back to the answer. This is going to be equaling, theta is the arc sine of x. You get 3/8 arc sine of x. And yes, according to Zusi, which I believe, she says that as far as web work is concerned, you can just jam an arc sine of x in for theta there and for theta there. If you're doing web work, you might avoid doing all this sine of 2 theta, sine of 4 theta BS, and just plug in the arc sine. Now, that's not the answer I would prefer.
I don't think anybody has web work.
Oh, I don't know.
I think
Oh, we're
it's
using
years.
Pearson.
Oh, sure. Well, but yeah, web work probably would take it.
Web work
Um,
stuff.
And then here we're gonna get 1/4 of our sine of 2 theta, which was 2 times x times that equals plus 2 times x times the square root of 1 minus x squared. Plus 1/32 times sine of 4 theta, which was 4 times x times the square root of 1 minus x squared times 1 minus 2x squared. 14. Yeah, that's terrible. But that's how you deal with a sine of 4 theta or a sine of 2 theta. So, but the thing to kind of keep in mind is really true. When you're doing these trig substitution problems, if you get sine of 4 theta or cosine of 4 theta, you can't deal with that other than by doing this double angle.
Could you show me where you did the double angle?
Well, like right here. If that is the double angle formula. I'm just saying sine of twice an angle
Yeah,
is 2 times sine of the angle times cosine of the angle. That is the formula.
okay.
Right, because I don't know what sine of 2 theta is,
Right.
but I definitely know from this triangle what sine of theta is. It's x.
Okay,
And what
okay.
cosine of theta is, it's square root of 1 minus x squared.
That makes.
And did you use that in the integral?
I didn't use it in the integral, I used it at the very end when I was changing back from theta, it's not the variable I started with, to x.
Okay.
Yeah,
What part of all this is converting sine of 4 theta to x?
this part right here.
I'm gonna take the.
Yeah. I mean, and also, really all of this, because you have to have this triangle.
Yeah,
I mean, yeah, and you can convert sine of any multiple of theta, really. You usually only run into even multiples though. So even multiples will, I mean, if you done it with the trig substitution, you're not typically gonna end up with an odd multiple of your angle. You will end up with even multiple sometimes when you do like this trig 1 plus 2 cosine theta over 2 or cosine 2 theta over 2. Right, when you do a trig where you get a cosine of 2 theta, that's what's making the sine of 2 theta or sine of 4 theta show up. Forgot my water. Well, questions about this? Anything really? Yeah, man.
So is there a way, you said we don't get odd angles, but if we did get odd angles, let's.
Yep.
Some problem. Is there a formula for?
Yeah, so if you had to deal with sine of 3 theta, even though I don't imagine that would come up, you would use the angle sum formula. So sine of A plus B is sine A cosine B plus sine B cosine A. So I write this as sine of theta plus 2 theta, and then I write that as sine of theta cosine of 2 theta plus sine of 2 theta cosine of theta. And then I have to use the double angle formulas for sine of 2 theta cosine of theta. It's just a lot of work. There's probably some like known formula for taking like sine of n theta and writing it as something with cosines and sines of theta, but I don't know.
Where does, how come the cosine comes in?
So I'm using the very general formula. So these trigger identities, at some point, someone should have shown you. That might not have actually happened though. So really, these double angle formulas, sine 2 theta and cosine 2 theta, come from these angle sum formulas. The sine of A plus B is sine A cosine B plus sine B cosine A.
Okay.
And it's a minus here, it's a minus here, and then there's also one for cosine. Cosine of A plus or minus B is cosine A, cosine B minus plus sine A, sine B. Those formulas are really how we get those formulas. Forget these, fun times.
I really hope we don't have to do this on the exam.
No, that's not an exam question,
No, he literally told us we should be prepared.
unless the Delta teacher.
Who's your teacher?
Hunter.
Oh, really? That's easy.
So much more.
Huh?
Turan is so much better. I miss him.
Really? Trend? I didn't have trend
Really?
for 21A.
Yeah.
I didn't have trend. I had a graduate student.
Okay.
Who did you have?
It was Eli. He was really difficult too, but
Who did you have?
Okay, so let's see here. We wanted to talk about, oh, that's the wrong folder. A whole lot wrong today. So last time we were talking about integration by partial fractions.
Yeah.
Okay, so partial fraction. We pretty much covered most of the things that can happen last time. So again, I'll remind you, partial fraction has to be a rational function. You should always check to make sure you can't do a u sub first. And then you need the degree on top to be less than the degree on the bottom, and you have to be able to factor the bottom. So what if we had something like the integral of x squared minus 1 over x squared minus 4? The degree on top isn't smaller. So before we can even think about using partial fractions, what we should always do if the degree on top is bigger than or equal to the degree on the bottom is do polynomial division. This one's not too terrible, right? X squared goes into x squared one time. 1 times x squared minus 4 is x squared minus 4. Subtract. And then x squared minus x squared is 0. -1 minus minus 4 is positive 3. So we can rewrite the integral as the integral of 1 plus 3 over x squared minus 4. One, we know how to anti-differentiate. And the 3 over x squared minus 4, that's where we're going to then use partial fractions because we can factor them.
Could you explain how to do polynomial division again?
Yeah.
I've done that here.
In fact, so let's finish this example, and then we'll do another example where the polynomial division is more intriguing. So I'm going to make something up. It's probably going to come out terrible. It's fine. So partial fraction decomposition, right? We do 3 over x minus 2 times x plus 2 equals to a over x minus 2 plus b over x plus 2. And then we multiply both sides by the common denominator, which is x minus 2 times x plus 2. Let's use other colors as other colors. We multiply the whole thing by x minus 2 times x plus 2. On the left-hand side, we always just get the numerator. Always what's going to happen. On the right-hand side, x minus 2 times x plus 2 times a over x minus 2, the x minus 2's cancel. and you get a times x plus 2. And then over here, the x plus 2's cancel and you get b times x minus 2. And then, and I can't stress this enough, you should always do it the way I say you should do it, which is, so you can do whatever you want later, but whenever you do partial fractions, you should always start off by using the nice values of x. It's super easy. It's always going to give you one or two things at least. So here, what I mean is I can set x equal to something that will make one of those things 0. Or really all but one of those zeros, what I'm actually saying. So if x is -2, I have 3 on the left, and a times 0 plus b times -4. So b is -3/4. And then similarly, setting x equal to +2, I get 3 equal to a times 4 plus b times 0. So a is equal to 3/4. It's pretty common that when you're doing partial fractions, if your constants start being fractions themselves, they usually have the same denominators or denominators that are pretty similar. Like you can get a common denominator really quickly. So this ends up becoming x plus the integral of a, so 3/4 over x minus 2 plus b -3/4 over x plus 2. And then we can integrate that pretty straightforwardly. You get x plus, this is going to be 3/4 natural log of the absolute value of x minus 2 minus 3/4 times the natural log of the absolute value of x plus c. Yeah.
But if that was the integral of 3 over x minus 2 and then x plus 2 squared, it would be a over x minus 2 plus b over x plus 2 plus c over x plus 2 squared. Okay.
So whenever you have what you're calling, or what you're referring to as a repeated linear factor, you always have all the highest power of that and then all the lesser powers down to 1. Yep. Let's look at another example. Am I going to make something up that's going to be good, or is it going to suck? Let's see here. Sure, let's try something like sure. Let's see, we're going to make something up that might be really awful. We'll find out. X to the 4th over x to the 4th plus 1 over x cubed plus x. That's interesting. Okay, that's what we want to integrate. And notably, 3 on top is larger than or equal to. Remember the equal to, right? If it's equal to, you also do this. People forget that sometimes. 3 on top is larger than or equal to, so we're going to do the polynomial division. So the way polynomial division works, I like the white chalk, but I feel like it's kind of easy to mistake it for other things that are being written. So let's do that. I'm going to do x to the 4th plus 1 divided by x cubed plus x. But really what I should do to make this not as terrible is you want all the missing terms, meaning I should really write this as x cubed plus 0x squared plus x. I don't need the plus 0 at the end. Dividing into x to the 4th plus 0x cubed plus 0x squared plus 0x plus 1. Just to make it so things line up nicely. You don't have to do this if you can see where things go, but just be careful. So then you ask yourself, you can ask it the regular division way, you're like, how many times does this go into this? But the better question to ask yourself is, what do you multiply by x cubed to get x to the 4th? The answer is x. I don't care where I put it, it doesn't matter. And then you multiply this thing by all of this. So x times x cubed is x to the 4th. X times 0x squared, that's gonna be boring. Sorry, if you make it up, and then you get a boring answer. 0x cubed, and x times x is x squared. Good so far?
So there's one x cubed, right?
Right, so basically, the divisor, you always want to write all of it in the standard way, meaning highest powers first and then lesser powers. And you're always just asking, what do you multiply by the thing with the highest power to get the first term there?
Wouldn't it be a 1, not an x on top?
Well, what's 1 times x cubed?
Oh, so x times x cubed is x to the 4.
Right,
Okay.
exactly. And then x times 0 x squared is 0 x cubed, and x times x is x squared.
Okay.
Then we subtract. That minus that 0, that minus that 0, 0 x squared minus x squared is minus x squared. Bring down the next terms, repeat the process, but the process is over because the thing I have now is a lesser degree than the thing I'm dividing by. There isn't any x to a positive power I can multiply by x cubed to get x squared. So I stopped. So the way I'm going to write this is I'm going to say that x to the 4th plus 1 over x cubed plus x is equal to x. I think something stupid. Okay. Plus negative x squared plus 1 over x cubed plus x. So it's always the quotient plus the remainder divided by the divisor.
Why isn't it divided by the dividend, if that's what's,
Oh, maybe that's the same name for it. I think that's the divisor or dividend.
I mean, the thing inside of the little house.
Well, because we're not dividing by the dividend. The dividend is what is getting divided into. Right? If you look at the fraction, the x to the 4th plus 1 is on the top.
Oh,
So the dividend is the thing we are dividing into, not dividing by.
okay.
The divisor is the thing we're dividing by. So what really this is representing is we did the division and we got that this divided by this was x. And then this remainder still needs to get divided by the divisor. We haven't done that division yet, and we're not gonna. Okay, so then that's what we're gonna do. We're gonna rewrite our integral as the integral of x plus, I might write that as, yeah, I'm being annoying, 1 minus x squared over x cubed plus x. Then we're gonna do partial fractions. I've got 1 minus x squared over, that does factor, not very nicely, is x times x squared plus 1. So I'm gonna write that as a over x plus bx plus c over x squared plus 1.
Why is it bx plus c?
Because x squared plus 1 is what we call an irreducible quadratic factor. And whenever you have something like that that doesn't factor any further, or that doesn't have any zeros, you have to have this bx plus c thing to make the algebra work. Essentially, if you just had b over x squared plus 1, you tried to solve for a and b, you would get a or b having to equal 2 different numbers, and it doesn't work. Then we multiply both sides of the common denominator. So we're gonna get 1 minus x squared equal to a times x squared plus 1 plus bx plus c times x. In fact, yeah, I will just point it out, right? If I just had a constant there instead, I would need that c was equal to 0, because I have 0x on the left, and I need that a is equal to both -1 and +1. Not gonna work. That's why I need the x plus c there. So then, use your one convenient value of x, which is what? My only nice convenient value of x here.
0.
So if I plug in 0, I get 1 minus 0 on the left. I get a times 1 plus 0 on the right. So a is equal to 1. And then I'm going to equate coefficients as my go-to method. So I'm looking at this, I'm seeing, oh, the highest power of x on either side is x squared. the left-hand side, I have a negative x squared. On the right-hand side, I have an a times x squared plus a b times x squared. So I can say that -1 has to equal a plus b. But since I know that a is equal to 1, I can say that -1 minus 1, so -2 is equal to b.
I'm a little confused on that.
Sure. So what I'm really doing, although I'm not actually doing it because I'm lazy, is I'm multiplying out each side. So I'm saying on the left-hand side, I have a negative x squared plus 0x plus 1. On the right-hand side, I have a ax squared plus a bx squared, so an a plus b times x squared. And then I have a c times x. And then I have an a times 1. What we're really saying is each coefficient of each power of x has to be the same on both sides. So this -1 here has to equal a plus b here.
Okay.
And similarly, we're going to say that c has to equal 0 because the coefficient of x on the left side, the coefficient of x is 0. On the right hand side, the coefficient of x is c. And then we're done. You can also say that a has to equal 1 because the constant term on the right has to equal the constant term on the left. So then we can go back and say this is going to equal the integral of x, and then we're going to have a over x, and a was what, 1? Yes. Plus 1 over x plus -2x over x squared plus 1. Right? We're getting a over x plus bx plus c over x plus 1. Our a is 1, our b is -2, our c is 0.
So to get the b and the c, you
Mhm.
plugged in x squared for x?
I didn't plug in x squared. I looked at both sides of the equation and I asked the question, what is the coefficient of x squared? So on the left-hand side, what is the coefficient of x squared?
I don't know, I'm confused what you did there.
Sure. So if I think of this as 1, or I think of this as -1 times x squared plus 1, what's the coefficient of x squared? Well, I got a -1. On the right-hand side, if I multiply,
Oh, I see what you're saying.
right, on the right-hand side, if I multiply this up, I have an ax squared plus a plus a bx squared plus cx. On the right-hand side, the coefficient of x squared is a plus b. And for polynomials to equal each other, it has to be the case that distinct powers of x have the same coefficient. There is no other way that these things are always equal to each other for every value of x, unless the coefficients of each power of x are the same.
Is that how you group them two up in the?
Exactly, that's exactly how I group them up here.
Oh, okay.
All right, I got x squared, x, constant, constant. You don't have to do it this way. You can do a different thing that some people find, I'll say conceptually easier, but computationally more challenging. So you could just pick other values of x if you wanted to. You could x equal to 1 and x equal to, I don't know, -1 and plug those in and solve for b and c. That would also work.
Can you plug in what you have for A too?
Yeah, well, you have to. Yeah. So but the other way you could attack this if you really wanted to would have been to say, well, okay, I've got a equal to 1, and then I'm just going to pick whatever, I'm going to pick x equal to anything but 0. So I pick x equal to 1. On the left hand side, I get 1 minus 1, so 0. On the right hand side, I get a is 1, so I get 1 times 1 plus 1 plus bx plus c by plugging in 1 for x. I'm getting plus b plus c. So b plus c equals -2, and I need another equation, so I pick some other value of x, like -1. I plug in x equal to -1, I still get 0 on the left, then I get a times 2, so that's 1 times 2, and then I'm gonna get b times -1 plus c, all times -1, so I'm still gonna get a b, but now I'm gonna get a minus c. And then you can solve the system of equations and then you're getting b equal to -2 and c equal to 0. That works, and it's actually not too terrible here because we have what I would consider a relatively small system. And we only have 3 things we're trying to find. But as the number of things you're trying to find gets larger, doing it this way, where you're just picking more and more values for x, gets to be really kind of just nasty. So I would always recommend equating coefficients because it's usually not as much things to keep track of. But it's totally in actuality, you can choose whatever you want.
Does it matter what number you use, or is it kind of like the guess how many?
It's not, you can use any number you want. I'm always trying to pick numbers that are small. Because then when I plug it in, things are gonna not be super huge. So I'm always picking numbers that are close to 0, right? Plus or minus 1, plus or minus 2, plus or minus 3, these are my go-tos, depending on what I've got, right? Like if I have x minus 4, I might pick 5, because I probably don't need 4. Just 5 minus 4. But yeah, I'm trying to pick things that make it small, but technically you could pick x equal to 30 and x equal to -15, and that would have given you the right answer. So then finally, to integrate this, we're gonna get x squared over 2 plus the natural log of the absolute value of x. And I see perfectly here a minus the integral of du over u, which is the negative natural log of the absolute value of u, which is going to be negative natural log of the absolute value of x squared plus 1. This comes up so much that you should just get used to seeing it being like, oh yeah, the antiderivative of 2x over x squared plus 1 is the natural log of the absolute value of x squared plus 1. Think about the derivative of this. The derivative of the natural log of stuff is 1 over the stuff times the derivative of the stuff. There you go. Or you can do the u stuff, right? But it's something that comes up so frequently that you probably won't get tired of doing it because you'll be like, oh yeah, I've seen this one like 10 times. Let's not do each other. Questions about any of that? Yeah.
What happened to the 2?
So if I do the u sub, my u is x squared plus 1, and my du is what? 2x dx. I'll also point out, I know I said it before, I'll say it again. If you look in the answers of the textbook, a lot of times they'll write this as a parentheses because x squared plus 1 is already always positive, so you don't actually need the absolute value.
Thank you, James.
Go on, man. All right, yeah, I have something else in mind. Where'd you go? Oh, those are all terrible. Let's look at this. Yeah. Sure. Chalk, yep, good old chalk. Let's look at, oh yeah, I saw that other problem. Sorry, I have to think about it for a second. Sometimes you have to complete the square. So for example, and I've seen this come up in some really weird ways, especially where there's some really weird Weber problems to discuss or whatever. Let's say we want to do the integral of, let me think for a second here. So let's actually, I want to point out, you all know this integral. You could do this with a trig sub, the integral of 1 over x squared plus 1. You should not do it with a trig sub. You just get to know that this is the arc, tangent. Okay. And then I will point out that if you have something like this, you could do this with a trig sub, you shouldn't. You can also do it with a u sub, meaning you can make it look like this by factoring out a 9 from the bottom. Factor out 9 from the bottom. Everything's still the same, just different. Then we factor out the 1/9. We have a 1 over x over 3 squared plus 1. So the idea here is you let u equal the x over 3, because then you will have a u squared plus 1 in the denominator. If you let u equal x over 3, my du is going to be 1/3 dx. I'm not using the quotient rule there. I'm just saying I have 1/3 times x, and the derivative is 1/3 times 1. So then I'm gonna rewrite this as 1/9 integral of 1 over u squared plus 1, and then my dx is gonna equal 3 du. Then I've got 3/9, which is 1/3. And the integral of 1 over u squared plus 1 is the arc tangent. And I end up with 1/3 the arc tangent of x over 3. Let's see. What I want to point out about this is, the problem is this comes up when you're doing integration or partial fractions. Here's what I mean by this. I could have had, let's say we had some terrible partial fraction problem. And we did all the partial fractions were blah, 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 blah. And we finally get to the place where we're like, okay, this is taking like 15 minutes of my life. Terrible, probably longer. And then I get to the point where I'm doing like the integral of, I don't know, like 1 over x plus 2 over x minus 1 plus 2x plus 3 over x squared plus 25. Gotten to this point. So I had some terrible problems. And this way, my brain is tired. I don't want to have to do, well, first of all, I have to break that up as 2x over x squared plus 25 plus 3 over x squared plus 25. And so we're going to get natural log of the opposite value of x plus 2 natural log of the opposite value of x minus 1 plus the natural log of the opposite value of x squared plus 25 plus 3 times. I really don't want to have to do like a trig sub or a u sub to do this. There's a pattern here which we can exploit, and that is that the integral of 1 over x squared plus 25 is 1 over 5 times the arc tangent of x over 5. Or more generally, as I'm sure in your textbook somewhere, the integral of 1 over a squared plus x squared is 1 over a times the arc tangent of x over a. And similarly, the integral of 1 over the square root of a squared minus x squared is the arc sine of x over a. There is no 1 over a in front of it, which always bothers me, but it's true. So the long story short here is that you typically are welcome to just have memorized those formulas. And you don't have to be like, oh, I see 1 over 9 minus x squared, 9 minus x squared. I don't need to do the trig sub x equals 3 sine theta and go through all that work. So the reason I bring this up is because sometimes you might have to integrate something like the integral of, let me think here for a second. Sure, 1 over, I don't want to be really terrible. No, I don't. X squared plus 6x plus 25. Doesn't factor. Really doesn't factor. Like not even like doesn't factor like x squared minus 7 doesn't factor, but it really does factor. X minus 3, 7 times x plus 3, 7. So I just want to point out, right? The x squared minus 7. No one can ask you this, but you can integrate this doing partial fractions. Because the bottom does factor. It factors dumbly, but this factors as 1 over x minus root 7 times x plus root 7.
Can't you do like a AX plus B7 situation?
No, it is not an x because here's what I want to point out. This x squared minus 7 is not an irreducible quadratic. It reduces, it factors, it has zeros, right? That parabola, if you just graph x squared minus 7, it shifts down and it has x intercepts. So really, when you hear the word does it factor or not, the actual question the words you should actually say in your head is, does it have solutions when you set it equal to 0? Does it have real zeros? X squared plus 4 doesn't, right? The zeros there are imaginary, plus or minus 2i. That means it's irreducible. That's when we have to do the arctangent thing. So irreducible just means if you set it equal to 0, it doesn't have any solutions. And that's the case here. This thing is irreducible. How can you tell if a quadratic is irreducible?
So y-intercept?
Not necessarily, because, well, it depends on, well, no, it's really about the vertex, but really it's about the discriminant of the quadratic formula. So if I set this equal to 0, and it doesn't factor, I start trying to solve by saying, oh, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2. And if this thing here, the discriminant, is negative, then we don't get real solutions. And it is negative. 36 minus 100 is definitely negative. So that's the real criteria for if you do this ax plus b thing or not. So problem is if that's the situation, you have to then complete the square. I'm going to rewrite this as the integral of 1 over x squared plus 6x plus, what's going to complete the square for me there? Divided by 2 is 3, 3 squared is 9. That completes the square. I'm not done, but what's x squared plus 6x plus 9 factor as?
Oh, 3.
Squared. That's why we call it completing the square. But then that's not the same, right? So what else do I need over here to make sure it comes out to be the same? Well, but 9 plus 25 is 34. So one way to do it is to be like subtract 9, add 25. Or you just be like 25 minus 9 is 16.
It's just as hard as it was in middle school.
Yeah, you never think like completing the square is gonna be that important in calculus, and you're like, oh, it is. Okay, so here's what we've got. We've got the integral of 1 over x plus 3 squared plus 4 squared. And I'm not actually going to do the u sub because it's silly. But if I did the u sub, I could let u equal x plus 3. And then my du would be dx. This is really the integral of 1 over u squared plus 4 squared. And then using my arctangent formula there, that's going to be 1/4 arctangent of u over 4. Right? People are going to typically be like, yeah, you can do this integral without showing a lot of work. But it's we're out of time. It's too bad because I could talk about this forever.